All right, so today we're going to be looking at convective heat transfer.
Oh, yeah?
And it's one of those things that, you kind of learn about in like high school physics or maybe like early on in college.
Right.
But, we're going to go a little deeper today.
Absolutely.
We've got a couple of sources here. Convective heat transfer, a concise briefing, and L2A convective heat transfer.pdf.
Excellent sources.
Yeah, should be pretty interesting stuff.
Yeah.
So this is like, the stuff that explains how like, a hot cup of coffee cools down or how a radiator, heats up a room or even like how, spaceships can survive re-entry.
Yeah, it really is quite fascinating how this one concept underpins so many different phenomena.
Yeah, so I guess let's start with the basics.
Sure.
Convective heat transfer, what we're talking about here is like the movement of heat between a surface and a fluid, like air or water,
Right.
when there's a temperature difference between them.
Absolutely.
But it's not just about like the temperature difference itself, right?
No, you're absolutely right. It also depends on how the fluid is moving.
Okay.
And so we can kind of distinguish between two main types of convective heat transfer.
Okay.
We've got forced convection and free convection.
Okay, so forced convection first.
Yeah, forced convection is when we use something like a fan
Right.
to force the fluid to move.
Okay.
And that speeds up the heat transfer. So think of like blowing on a hot spoonful of soup
Right, yeah.
to cool it down.
To cool it down.
Yeah,
Okay, that makes sense.
that's forced convection.
Okay, so what about free convection?
Free convection, sometimes also called natural convection.
Okay.
It's driven by temperature differences themselves.
Oh, okay.
So when a fluid heats up, it becomes less dense
Right.
and it rises, and then cooler, denser fluid sinks to take its place.
Yeah.
And this creates this natural circulation
Okay.
that carries heat away.
So like a radiator.
Exactly. A radiator warming a room, the heat rising from a hot stove, that's all free convection.
Okay, so it's like with forced convection, you're giving it a helping hand.
You're giving it an extra push.
You're giving it an extra push, and free convection is just kind of like letting it,
Let nature take its course.
yeah, let nature take its course.
Yeah.
Okay, so we've got these two kind of different ways that convective heat transfer can happen.
Right.
But how do we actually like quantify this? How do we actually like measure this and know how much heat is being transferred?
So to really understand how it works mathematically, we need to bring in Newton's law of cooling.
Okay, Newton's law of cooling, yeah, our sources talk about that.
It's a fundamental principle here.
Yeah, and it basically says that the rate of heat transfer, also called the heat flux, and I think that's represented by Q with a dot over it.
Q dot. That's
Flow
so.
dot dot. Okay, so Q dot is equal to this thing called the convective heat transfer coefficient. I believe that's alpha,
Alpha, yeah.
times the difference in temperature between the surface and the fluid.
Exactly.
So the equation is like Q dot equals alpha times, and
Yeah.
then in parentheses, TS minus TF.
You got it. That's the foundation. And that convective heat transfer coefficient, alpha, that you mentioned is super important
Okay.
because it basically tells us how effectively heat is being transferred between the surface and the fluid.
Okay.
But here's the thing.
Okay.
Alpha is not a constant value.
Oh, so there's more to it than just like plugging some numbers into a formula.
Exactly. There are a lot more layers to it. Yeah,
Okay, that makes it a little more interesting.
definitely. Yeah, it's affected by a whole bunch of things like how fast the fluid's moving, the surface properties,
Yeah.
even the shape of the object.
Oh, wow. Okay.
Yeah.
So we need to like understand those factors in order to like really grasp how this heat transfer is happening.
Exactly. And that's where the concept of boundary layers comes in.
Boundary layers. Okay, yeah, our sources talk about these.
Yeah.
And they describe them as thin regions near the surface where like the fluid's velocity and temperature change like really drastically.
Right. So there are two types of boundary layers
Okay.
that we talk about.
Okay.
The hydrodynamic boundary layer
Mm-hmm.
and the thermal boundary layer.
Oh,
So the hydrodynamic boundary layer is where the fluid's velocity changes from zero at the surface due to friction
okay.
to the free stream velocity further away. So like imagine a river flowing past a rock.
Oh, okay.
The water right next to the rock is moving very slowly,
Right.
but further out in the river, the water's flowing freely.
Right.
That transition zone,
Yeah.
that's the hydrodynamic boundary layer.
Okay, I like that analogy. Okay, so then the thermal boundary layer, is that just the same thing but with temperature?
Exactly, yeah. So it's where the fluid's temperature changes from the surface temperature to the temperature of the surrounding fluid.
Okay.
And the thickness of these boundary layers really has a big impact on how efficiently the heat's being transferred.
Okay, so I'm starting to see the bigger picture here.
Good.
So our sources then go into this classic example of forced convection over a flat plate.
Right. A classic scenario.
Yeah.
Yeah, and this is where things can get a bit more complex, but bear with me. We often try to simplify things by assuming steady-state flow, incompressible fluid, constant material properties.
So we're kind of like creating an idealized scenario to try to understand the fundamentals.
Exactly, yeah.
Okay.
We have to simplify it somewhat to make the math manageable.
Right. Okay. And so even with those simplifications, we still need some pretty heavy-duty math to
I
like
do.
figure this stuff out.
Yeah, we need to use equations like the continuity, momentum, and energy equations.
Oh, yeah, that's the stuff I was a little worried about.
Yeah,
But there's something called the Blasius solution, right?
yes, the Blasius solution.
Which helps us with these calculations.
Exactly. Okay, so what is that?
So it's basically a way that mathematicians figured out how to solve those equations for a specific case,
Okay.
which is laminar flow over a flat plate.
Okay.
And it gives us a really accurate picture of how the fluid flows near the surface.
Wow. Okay, so that's pretty impressive. It sounds like we've got some pretty heavy hitters in the physics world working on this stuff. Yeah, there's a lot of really smart people that have been working on this for centuries
Yeah.
to figure it all out.
Okay, so to understand these solutions better, I think we need to talk about a few key players in the convective heat transfer game.
Yes.
Our sources talk about the drag coefficient,
Right.
the Nusselt number, and the Prandtl number.
Yes.
Mm-hmm.
These are all dimensionless numbers that help us make sense of these complex interactions.
Okay, I remember dimensionless numbers, they always pack like a ton of information into like a single value.
Exactly.
So what about the drag coefficient? What's that all about?
The drag coefficient basically tells us how much the fluid is resisting flowing over the surface.
Okay.
You know, like if you stick your hand out of a moving car window,
Right.
you
Yeah.
feel the air pushing against it.
Yeah.
That's drag.
Yeah.
The drag coefficient puts a number on that resistance.
So like a higher drag coefficient means like the fluid is stickier, it wants to cling to the surface more.
Exactly. And it turns out that the drag coefficient is related to another dimensionless number called the Reynolds number.
Okay.
And we can use the symbol Re, subscript X, for that one. And the Reynolds number basically tells us whether the flow is smooth and orderly,
Okay.
which we call laminar flow, or if it's kind of chaotic and swirling, which is turbulent flow.
So it's like the Reynolds number is kind of telling us like the personality of the flow.
Yeah, that's a good way to put it, yeah.
Okay. All right. So then what about the Nusselt number? What's that all about?
So the Nusselt number, nu, is a really crucial one because it compares how effectively heat's being transferred by convection versus just conduction within the fluid.
Okay.
Basically, it tells us how much the fluid motion is boosting the heat transfer
Right.
compared to if the fluid was just sitting still.
So like a higher Nusselt number means we're getting more bang for our buck in
Right.
terms of heat transfer?
Yeah, because of the fluid motion.
Okay, that makes sense. And the Nusselt number, that depends on the Reynolds number
It does.
that we just talked about.
It does.
And then another dimensionless number
Another one.
called the Prandtl number. Is that right?
That's right, the Prandtl number.
Okay, so I'm guessing the Prandtl number has something to do with the fluid itself.
You got, yeah, the Prandtl number basically tells us how quickly momentum spreads through the fluid
Okay.
compared to how quickly heat spreads.
Okay.
So it's really helping us understand how the fluid's internal properties
Yeah.
affect this whole heat transfer process.
Okay, so we've got these like three different numbers.
Three powerful numbers.
Drag coefficient,
Yep.
Nusselt number,
Okay.
Prandtl number.
Got it.
And they're all kind of giving us like different pieces of the puzzle to understand how efficiently heat is being transferred.
That's a great way to think about it, yeah. And these are really essential for engineers
Okay.
because they allow us to predict and analyze convective heat transfer in all sorts of applications.
That makes sense, but I'm curious, are these concepts like flow resistance, so like drag coefficient, and heat transfer, which is like the Nusselt number?
Right.
Are those completely separate things, or is there some kind of connection between them?
That is a brilliant question, and it leads us to a really elegant concept called the Reynolds analogy.
Okay, the Reynolds analogy, I'm all ears.
Yeah, so the Reynolds analogy shows us that there's actually a direct relationship between turbulent momentum transfer, which relates to that drag force,
Okay.
and turbulent heat transfer.
Okay.
So remember how we talked about those chaotic eddies in turbulent flow?
Yes.
Well, it turns out that those eddies are responsible for both resisting the flow
Okay.
and transferring heat.
So by understanding like how much the fluid resists flow, we can actually like gain insights into how well it's going to transfer heat.
Exactly.
Well, it's amazing.
It's a really remarkable connection.
Yeah.
It highlights just how elegant physics can be.
Yeah, that's awesome. Okay, so we've got these dimensionless numbers. We've got the Reynolds analogy to help us analyze this stuff.
Right.
But is there a way to figure out that all-important heat transfer coefficient alpha, without having to solve all those crazy equations.
There is.
Because I am all about shortcuts.
You're in luck.
Okay.
Because scientists and engineers have developed something called Nusselt number correlations.
Okay.
And these are basically formulas based on experimental data that let us estimate the Nusselt number,
Okay.
and therefore alpha, for different flow situations.
So these are like our cheat codes.
Exactly, they help us bypass those complicated equations.
Awesome.
So for example, for laminar flow over a flat plate,
Okay.
there's a specific correlation that involves the Reynolds number and the Prandtl number.
So we can just like plug those in and get a pretty good estimate of how much heat is being transferred.
Exactly.
Okay, are there correlations for other situations like turbulent flow or like flow in pipes?
There are different correlations for various flow regimes and geometries.
So like we've got this toolbox
Yeah.
full of like specialized tools
Sure.
to tackle different heat transfer problems.
That's a great way to put it.
This is great, but I have a feeling like these correlations are based on like specific assumptions.
They are.
So there must be some limitations to how accurate they are.
You're right, they are approximations.
Okay.
And they may not be valid for every single situation,
Right.
but they give us a really powerful way to understand and predict convective heat transfer without getting bogged down in the complexities of solving those full-blown equations every time.
Okay, this is all blowing my mind. We've covered so much already.
I know, right?
But what's next? Where do we go from here?
Well, in the next part, I think we should move from these fundamental concepts to some more practical applications.
Okay.
We'll see how convective heat transfer is at play in things like heat exchangers, electronics, cooling, aerospace engineering, even in the natural world, in the atmosphere and oceans.
Wow, okay. I'm excited. I can't wait to see how all of this ties together.
It's really incredible how this one concept impacts so many different aspects of our world.
Yeah, it really is. Okay, so listeners, stay tuned for the next part of our deep dive as we explore the fascinating world of convective heat transfer
It's going to be a good one.
and see how it shapes our lives in countless ways.
I can't wait.
All right, see you then.
See ya.
Okay, welcome back.
Back for more.
I'm still like processing all that stuff from the first part. It's pretty amazing.
It's a lot to take in.
It is.
Yeah.
But now I'm ready to see like how does this actually play out in real life?
Yeah, well, get ready to have your mind blown wide open,
Okay.
because we're about to delve into some truly incredible applications.
Okay, great.
Yeah.
So our source material goes into forced flows in pipes and ducts.
Okay.
Kind of like we're going from that gentle breeze over a flat plate to like a rushing river
Exactly.
flowing through a channel.
A fantastic analogy.
And understanding heat transfer in these like confined spaces like pipes and ducts, that's got to be important for so many things.
Oh, it's essential. For so many things like designing HVAC systems to keep us comfortable, optimizing industrial processes, you name it.
It's amazing how this seemingly abstract concept is so like intertwined with our daily lives.
It really is.
But before we jump into all these applications, our sources introduce another Reynolds number.
Right.
This time it's Re subscript D.
Red.
Red D, okay? And this one is specifically for flow in pipes.
For pipes, exactly.
So remind me again, how does the Reynolds number help us understand the flow?
So remember how the Reynolds number helps us figure out whether the flow is laminar, nice and smooth, or turbulent, all chaotic and swirling?
Right, okay, yeah.
So red D is the same idea, but tailored for pipes.
Okay.
And it takes into account things like the average velocity of the fluid, the pipe's diameter, and the fluid's viscosity.
So are you saying that like the pipe's diameter can actually influence whether the flow is laminar or turbulent?
Exactly.
Wow.
Imagine a narrow pipe versus a really wide pipe. If you have the same amount of fluid flowing through both, the fluid's got to move much faster in the narrow pipe
To keep up.
to keep up, right? And that increase in velocity can actually push the flow from laminar into the turbulent regime.
Oh, that's so cool. So the shape of the pipe
The geometry.
actually affects how the fluid's behaving.
Absolutely.
Okay, that's fascinating.
Yeah.
So our sources then talk about how when we're analyzing heat transfer in pipes, we often focus on the average temperature of the fluid,
Right.
often denoted as like Tim.
Exactly.
So why do we do that?
Well, it helps to simplify things a little bit, especially when we're dealing with turbulent flows where the temperature can vary quite a lot across the pipe.
Okay, so we're kind of assuming it's uniform just to make things a little easier.
Yeah, it's a simplification, but it still gives us a lot of valuable insights.
Okay, and so like the main question then becomes, how does this average temperature change as the fluid flows along the pipe, especially when the pipe wall is kept at a constant temperature?
Right, that's the key question. And to answer that, we have to think about how the heat flux, or the rate of heat transfer, is actually affecting the fluid.
Okay.
And according to our sources, it leads to a change in something called the enthalpy of the fluid.
Enthalpy. Okay, that sounds kind of intimidating.
Yeah, it's a bit of a fancy word, but it really just means the total energy of the fluid.
Okay.
And that includes both its internal energy and the energy that's related to its pressure and volume.
Okay, so when heat is transferred to the fluid, its enthalpy increases.
Exactly. It's like the fluid's getting an energy boost from the heat.
Got it.
And to actually quantify how much heat is being transferred, we need to introduce the local convective heat transfer coefficient, often represented by alpha subscript x.
Okay, so that's telling us how much heat's being transferred at a particular point along the pipe.
Right, based on the temperature difference between the wall and the fluid.
Okay, but in like a real world application, wouldn't we want to know like the overall heat transfer across the whole pipe?
That's a great point.
Hey.
And that's where the average convective heat transfer coefficient comes in.
Okay.
It's basically taking the average of all those local coefficients along the entire pipe length.
So it gives us the big picture.
Exactly. And our source material actually provides an equation to calculate this average coefficient.
Oh, okay.
And it involves something called the mean logarithmic temperature difference,
Okay.
which might sound complicated.
It does.
But it's basically just accounting for the temperature changes at both the inlet and outlet of the pipe.
So it's like taking into account the whole temperature journey of the fluid.
You got it.
That's pretty neat.
Yeah.
Okay, so let's talk about those Nusselt number correlations again.
Okay.
They're like our cheat codes, right? For understanding heat transfer.
Exactly.
Are there specific correlations for pipe flow?
Absolutely.
Okay.
And just like with the flat plate, we've got different correlations for laminar flow and turbulent flow.
Yep.
So for laminar flow in a fully developed pipe flow, meaning the flow has settled into a nice stable pattern,
Okay.
the correlation is actually quite simple. No D equals 3.66.
Wait, so the Nusselt number is just a constant value in this case?
It is
Yeah.
surprisingly straightforward.
That seems too easy.
I know, right? But it's important to remember that this only applies to the fully developed region of the pipe,
Okay.
near the entrance of the pipe where the flow is still developing.
Right.
The heat transfer coefficient is actually much higher,
Oh, okay.
and it decreases gradually until it reaches that constant value of 3.66.
So the heat transfer is more intense at the beginning and then it kind of like chills out as the flow gets going.
Exactly.
Okay.
And for those entry regions where the flow and the temperature profile are still developing, there's a different correlation
Oh, okay.
that involves both the Reynolds number and the Prandtl number.
So even within laminar flow, we've got different situations that require different correlations.
Exactly.
Okay, so what about when the flow in the pipe becomes turbulent?
So when it becomes turbulent, the correlations do get a bit more complex,
Okay.
but they still provide us with a valuable tool to estimate the Nusselt number and therefore the heat transfer coefficient.
Our sources give us a correlation for turbulent flow in pipes with Reynolds numbers in a certain range,
Right.
and it shows us just how important the flow velocity is for heat transfer, right?
Exactly. The faster the flow, the higher the Reynolds number, and the more efficient the heat transfer.
That's awesome. We've been talking a lot about circular pipes. What about like channels with different shapes like rectangles or triangles? Do those correlations still work?
That's a great question. And luckily, we can actually apply those same correlations to non-circular channels by using something called the hydraulic diameter,
Okay.
which is essentially a way to characterize the flow area in any type of channel.
So we can use the same tools we've developed for circular pipes for these more complex shapes.
Exactly. It's very versatile.
That's so cool.
Yeah, but there's another really important factor we need to consider, and that is what happens when the fluid's properties change significantly with temperature.
Okay, and this happens a lot with liquids, right?
Yes, especially with viscosity.
Okay, so how do we account for that?
Well, our sources mention that we need to account for those changes in viscosity,
Right.
and we can often do that by using the average temperature of the fluid and applying some correction factors.
Okay, so we're just refining our calculations to
Yeah.
better match what's actually happening.
Exactly.
Okay, so we've talked a lot about forced convection,
We have.
but what about free convection, our old friend?
Oh yes, free convection, driven by those buoyancy forces
Yeah.
caused by temperature differences.
Like that rising plume of steam from my coffee.
Exactly.
Or the warm air circulating in a room.
That's free convection all around us.
It really is everywhere, and while analyzing it can be pretty complex.
It can be.
Our sources do give us some fundamental insights, right?
They do.
So remind me, in free convection, the fluid motion is driven by those density variations.
Exactly. The density variations that are caused by those temperature differences.
Right, warmer fluid is less dense,
less
So it
dense,
wants to rise.
wants to rise.
Cooler fluid is more dense, so it wants to sink.
It sinks, exactly,
Creates that circulation.
that natural circulation pattern. Right.
And so what's the key parameter that helps us understand the strength of this free convection flow?
So the key parameter here is called the Grashof number, GR.
Okay, another dimensionless number
Another one for our collection.
to add to the list.
Exactly.
Okay, so what's so special about the Grashof number?
So the Grashof number basically gives us a ratio of the buoyancy forces, which are driving the flow, to the viscous forces, which are resisting the flow.
Okay, so it's like a battle between buoyancy and viscosity.
Yeah,
And the Grashof number tells us who's winning.
exactly. Great way to think about it.
Okay.
And just like with forced convection, we've got Nusselt number correlations for free convection that help us relate the heat transfer to the Grashof number and the Prandtl number.
Our sources give us correlations for different situations,
They do.
like a vertical plate.
Right.
And so these correlations give us a way to estimate the heat transfer
They do.
in situations where the fluid's motion is just driven by those temperature differences.
Exactly.
Okay, this is awesome.
Yeah.
I feel like it's all starting to make so much sense now.
Good.
We've covered forced convection in pipes. We've covered free convection. All these awesome dimensionless numbers that
Yeah.
help us like unravel all these complexities.
I think we've laid a really solid foundation.
We have.
And now it's time to actually see how all this knowledge is applied in specific real-world examples.
Okay, part 3. Here we come.
I'm excited.
Okay, so welcome back to the final part of our deep dive into convective heat transfer.
All right, the grand finale.
I am so pumped to actually see how all this stuff we've learned like comes to life in actual real-world application.
Oh yeah, get ready for some mind-blowing examples.
All right, bring it on.
Because we're going to see how convective heat transfer is like the key player
Okay.
in everything from everyday appliances
Right.
to cutting-edge technologies and even like
Right.
the natural processes that
Yeah.
shape our whole planet.
Okay, that's awesome. All right, let's start with something that's probably like running in a lot of our kitchens right now.
Okay,
Refrigerators.
the trusty refrigerator.
Our sources mention that refrigerators rely heavily on these things called heat exchangers, which are devices that transfer heat between fluids.
Right.
And it seems like convection is like at the heart of it all.
Absolutely.
So what are heat exchangers all about? I know they use the temperature difference between two fluids to like move heat around, but how do they actually work?
So imagine you've got two fluids at different temperatures,
Okay.
and they're flowing near each other, but they're separated by a solid wall.
Okay, right.
The heat exchanger's job is to make it super easy for heat to transfer
Okay.
from the hotter fluid to the cooler fluid through that wall. And this is where convection comes in.
So it's all about like maximizing that convective heat transfer between the fluids and the surfaces inside the heat exchanger.
Exactly. And this means all those concepts we've been talking about.
Yeah.
Boundary layers, Nusselt number, the Reynolds analogy,
Right.
they're all super important
Okay.
for designing efficient heat exchangers.
So engineers are like using all this knowledge to design the geometry and flow paths within the heat exchanger to make that transfer as efficient as possible.
Exactly. They might use things like fins or baffles to increase the surface area
Oh, okay.
or create turbulent flow
Right.
to boost that heat transfer.
So they're like conducting a symphony of fluids and heat,
I love that. That's a great way to put it.
carefully like orchestrating every movement to get that heat where it needs to go.
Exactly.
Okay, let's zoom in on another application that's probably pretty close to a lot of us right now.
Okay, let's do it.
Electronics cooling.
All right. My laptop can get so hot, especially when I'm gaming.
Oh, I hear ya. It's like I can hear the fans whirring away, trying to keep things under control.
Right. And as electronic devices become more and more powerful and more compact,
Right,
managing that heat they generate
right.
becomes a huge challenge.
Yeah, if it overheats, it's not good.
No, it can really reduce performance, even shorten the lifespan of the device.
So convective heat transfer to the rescue.
It is. It's our digital savior.
Okay, how does it work?
So engineers use a lot of really clever techniques that leverage convection.
Okay.
One common approach is incorporating heat sinks.
Okay. Heat sinks.
You know, those metal structures with a large surface area designed to dissipate heat.
Yeah, I've seen those like fin-like things on the processor in my computer.
Exactly. They look like miniature radiators.
They do.
And those fins increase the surface area that's in contact with the air,
Right.
allowing for more effective convective heat transfer.
Okay.
And to boost things even further, they often use fans to force air over those heat sinks.
It's like giving those hot components a nice cool breeze.
Exactly.
Okay, and then for like really high performance computers, I've heard of liquid cooling systems.
Yes, liquid cooling.
Is that also based on convection?
Absolutely.
Okay, how does that work?
Liquid cooling can be way more effective than air cooling,
Right.
especially for those components that generate a lot of heat.
Okay.
It involves circulating a liquid coolant
Right.
through channels in contact with those hot components.
Okay.
And that liquid absorbs the heat and carries it away.
So it's kind of like a car's radiator.
Exactly, like a car's radiator.
Okay, that's awesome. So it seems like the more powerful our devices get,
Yes,
the more creative we have to get
we do.
with our cooling solutions.
That's right.
That's pretty amazing. All right, so we've seen how convective heat transfer is essential for like our everyday gadgets.
Right.
But it also plays a huge role in aerospace engineering, right?
Oh, absolutely. Think spaceships, rockets.
This is where we're really pushing the limits of engineering. I
Yeah.
can't even imagine the heat generated during like space reentry.
Oh, it's intense.
It's mind-boggling to think about how they survive those temperatures.
Well, and that's precisely why engineers rely so heavily on the principles of convective heat transfer.
Okay.
They design heat shields using materials with high thermal conductivity
Right.
to absorb and dissipate that immense heat generated during reentry.
Okay.
And those shields are often shaped in really complex ways
Okay.
to enhance convective heat transfer away from the spacecraft.
So those heat shields are like super efficient cooling systems.
You could say that, yeah, it's really a testament to human ingenuity
Yeah.
and our understanding of heat transfer that we can design systems capable of withstanding such extreme conditions.
Absolutely. All right. So we've seen how these principles of heat transfer can be applied to these huge, like monumental challenges.
Right.
But it's not just about human-made systems, right?
That's right.
Convection shapes natural phenomena, too.
It does.
Like our sources talk about atmospheric and oceanic circulation.
Absolutely. Convective heat transfer plays a fundamental role in shaping our planet's climate and weather patterns.
Okay, yeah, I remember learning about these currents in school, but I never really connected them to this deeper understanding of heat transfer.
Right. Well, think about it. The sun's radiation heats the Earth's surface, but it does it unevenly.
Okay, right.
And that creates temperature differences,
Right.
which lead to warm air near the equator rising,
Okay.
creating low pressure zones, and then cooler air from higher latitudes rushes in to replace it,
Creating wind.
creating winds, weather systems. Exactly.
So it's like a giant planet-scale convection system.
You got it.
That's incredible.
Driven by the sun's energy.
And it happens in the oceans too, right?
In the oceans, too, warm water near the tropics flows toward the poles, colder water from the poles sinks and flows back towards the equator.
So these huge circulation patterns,
Massive circulation patterns,
all driven by convection.
all driven by convection.
That is wild. It's like the same principles that explain how my coffee cools down
I know, it's amazing.
are also responsible for these massive global phenomena that shape our planet.
It's a beautiful illustration of how the laws of physics work at so many different scales.
Yeah. All right. So this deep dive has been an incredible journey.
It has.
We've gone from those basic definitions and equations to exploring boundary layers,
Right.
dimensionless numbers, Nusselt number correlations.
Yeah.
And we've seen how it all comes together in all these amazing real-world applications.
We have.
It's like we've learned the secret language
It is kind of like a secret language.
of heat transfer
It is.
that helps us understand how heat shapes our world.
I couldn't have said it better myself.
All right, well, listeners, I hope you've enjoyed this exploration as much as we have.
Yeah, me too.
And I bet you're seeing convective heat transfer everywhere you look now.
I hope so.
Like in your kitchens, in your gadgets, in the weather, even out in space.
Absolutely.
It's amazing to think that even the most complex phenomena can often be explained by some pretty simple, elegant principles.
It's the beauty of physics.
It really is. All right, so until our next deep dive, stay curious, keep exploring, and never stop asking questions
Great advice.
about the amazing world around us.
Couldn't agree more.